Morning, student. Let's do something a little bit more crazy today. So we can say that this lecture is going to be considered Cartesian coordinate in 3D space. Uh, for those you might be wondering, uh, what do I need to know, or when do I take this? When do I take the lesson like this? Well, for the student want to take honor geometry, so let's say that student want to learn like 3D geometry, and also for student getting bored about after Cal 2 or Cal 1 want to take a look at that, some kind of a 3D space. So I think this one, it's linking toward Calculus 3, which is called the multivariable calculus. I think this one would be the first lesson student would be doing in Cal 3. And the majority of high school, we don't offer Cal 3 because that student can finish either AP Stats or taking other like engineering courses before they go to college. But few high school, like private high school or some other high school, they offer multivariable calculus. Like the school that I've been teaching for the last 14 years, like 2 years ago, they tried to start it with multivariable calculus, but due to the number of low enrollment, so we only have few students registered for that. So that's why the class got canceled. So in the future, I plan to put some like Calculus 3 lecture video on YouTube, okay? So just stay tuned, and for those who would like to learn something like that. And here's one of the major important lesson, and that's one of the introductions for multivariable calculus. So 3D space. So for those students learning x-axis, y-axis, the z-axis, so in geometry honors, so a point in 3D space is given by the order triple, x, comma, y, comma, z, okay? So the x component, the y component, and then the z component. So you see that this one, once you plot that point, it's a point in the space, okay? Not on the xy plane, but in the space. So let's say that you want to plot the point 2, 3, 4. So you started with that 2 units on the x-axis, going forward, going to the outer, okay? And then 3 unit to the right, okay? Again, forward to the right, it's all considered positive. And then up for the z-axis, it's also considered positive. So it's 2 units forward, 3 units to the right, and then counted 4 units up. So point P would be plotting right here. And then what about -1, 4, -3? So -1, that means going backward on the x-axis, count 1 unit backward, and then 4 units to the right, and then down 3 units, so point P would be down here. Again, it's a point in the space. So in the reality, we just see like 3D x-axis, y-axis, z-axis. But once you go out to the space, so it's going to be hyperdimensional. It could be more than 3D, it could be more than 4D, so it's hyperdimensional. So scientists, they're saying that it's like 11 dimensions or 12 dimensions. So actually, in my opinion, it's actually more than 12 dimensions, okay? If we go to the galaxy, so it could be considered like an infinitely many dimension. Okay, so now here's the distance formula in the 3D space. So d squared, so that equals delta x quantity square plus delta y quantity square, and then plus delta z quantity square. As you may wondering, so delta x, is that the change of the distance of x? It is. And then delta y, that's just like y2 minus y1, the change of distance of y, and then z, then that'll be the change of the distance in z component. So let's say we do have a rectangular prism. And as you may see that we do have a cross-section area, the right triangle. So one is like this. So it's P1, P2, and Q. And the other one, a triangle is P1, QR. So P1, QR. So the one with the shaded region, the blue and the black. So they are both considered right triangles. Then we can use the Pythagorean theorem. So P1Q quantity square plus Q P2 quantity square, so that equals P1, P2 quantity square by using the Pythagorean theorem. So that would be the first equation. And then the second equation, we do have P1R quantity square. Again, P1R, that's just the line segment here. and then plus RQ1 plus RQ quantity square. So RQ quantity square. So here's the line segment. Once you take the square of this line segment, so combine it with the previous one. So we'll get that to P1Q quantity square. So once you substitute that equation 2 into equation 1, so you end up with this. So P1R quantity square plus Q RQ quantity square. So plus Q P2 quantity square. So that equals P1 P2 quantity square. So the reason why that I put a star here, so this one is very important. So this one is linking to the distance formula in the 3D space. So if P1 is the point x1, y1, z1, okay, and then P2 is another point x2, y2, z2, okay, so this one can be written this way. So Q and R, so Q is written x2, y2, z. Q can be written as x2, y2, z1 using that the component form, and then R can be written as x2, y1, z1. So one thing that we find out the difference of the distance here, so PR quantity square, so can be written as x1 minus x2 quantity square. So since y and z coordinates are the same, and then QR or RQ quantity square can be written as y1 minus y2. I should put in the quantity square right here, plus z1 minus z2 quantity square. So since these 2 points are on the same plane, so the 2D length formula. So P1, P2 quantity square, so that equals quantity x1 minus x2 square, plus y1 minus y2 quantity square, plus z1 minus z2 quantity square. And then once you solve for P1, P2, so basically this one is just the distance formula in 3D space. So what I'm showing you here, so this one is just the proof of the 3D space distance formula. So here's the little summary. So 1D, so that means, well, if 2 points given, so that means we can just make a straight line. So in order to find out the distance of the straight line, it's about absolute value of x1 minus x2, or you can just do that square root of the quantity, x1 minus x2 quantity square. And then in the 2D plane, so in order to find out the distance, so P1, P2, so that we're just using the regular distance formula. So square root of quantity x1 minus x2 square plus y1 minus y2 quantity square. And then 3-dimensional space, just like the one I showed the proof for. Okay, so P1, P2, so that equals square root of x1 minus x2 quantity square plus y1 minus y2 quantity square plus z1 minus z2 quantity square. So now let's do some example. So show that these points are vertices of an equilateral triangle. So you just plot the points. So once you connect them, so it's going to be equilateral triangles. It's a plane in the 3D space. So we'll talk about the graphing later. So you want to show that AB is the same as BC, is the same as AC. So we're using those formula. So the distance formula in the 3D space. So started with that distance AB. So 4 minus 1 quantity square plus 5 minus 7 quantity square, and then plus 3 minus 4 quantity square. So once you evaluate it, it's root 14. And then BC, so similarly, so you want to do something similar to this, which is 1 minus 2 quantity square plus 7 minus 4 quantity square plus 4 minus 6 quantity square. Evaluate it, you'll get root 14. And then for the last component, AC, so quite similar, so just plug in a number. As you can see that here, so the way that we subtract those numbers, we want to subtract the x value correspondingly, same as the y value, and same as for the z values. Okay, so once you end up with the distance, the magnitude, so then that will be considered root 14, root 14, root 14. So for spheres, so all points x, y, z on a sphere are a fixed distance. So r from the center. So let's say we do have a sphere, a balloon. So r equals square root of x minus h quantity square plus y minus k quantity square plus z minus l quantity square. So the equation of a sphere with the radius r and the center h, k, L, it's called r squared equals x minus h quantity squared plus y minus k quantity squared plus z minus L quantity squared. And then using the midpoint formula, we can find the center of the sphere. So it's x1 plus x2 over 2, comma, plus y1 plus y2 over 2, comma, plus z1 plus z2 over 2. So that would be the midpoint formula, the way to find the center of the sphere. So find the center of the radius, find the center and the radius of this sphere. So first thing that you want to do, you want to group the like term, and then you want to complete the square for each one of those x, y, z component. So once we do that, we do have x squared plus 2x. The reason why that I get 1, because that's b over 2 quantity squared, so it's 2 over 2 quantity squared. You can always refer back to the conic sections video, the way that I show you how to complete the square for the conic sections. And then y squared minus 6y, so b over 2 quantity squared, so we got negative 6 over 2 quantity squared, we got 9. And then z2 minus 10z, so negative 10 over 2 quantity squared, so we got 25. Whatever the number that we add on the left-hand side, we want to do the same thing on the right-hand side. So once you combine it, so we do have the equation of a sphere. And then the center, it's right at negative 1, 3, 5, with the radius 1. So find the equation of the sphere, and that has the diameter of negative 4, 2, 1, to 8, 3, 6. So from one point to another point in the 3D space. So center of a sphere is a midpoint of any diameter. So we use the midpoint formula to find the center. So once we get into the center, and the next thing that you want to do, you want to find the radius. So the radius is always the diameter divided by 2. So in order to figure out the distance of the diameter, we use the distance formula of the 3D space. So it's negative 4 minus 8 quantity squared plus 2 minus 3 quantity squared plus 1 minus 6 quantity squared. So once we get that to the distance of the diameter, we divide it by 2. Then we'll get the radius. So once we get the radius, we already found the midpoint, the center of the sphere. So we basically just put it back to the equation of a sphere. So again, the equation of a sphere, which is given like this. So plug in the number. So here's what we got. X minus 2 quantity squared plus y minus 5 half quantity squared. And then plus z minus 7 half quantity squared. So that equals radius squared, which is 85 over 2. So linear equation in 3D space. So here's the one, ax plus by, so that's pretty normal in 2-dimensional. But with the other component, z, so plus z, cz equals d. So the equation of a plane in the 3D space. If that's 1D, so linear equation is example as 3x equals 5. So that's just a point. In a 2-dimensional plane, so example like 3x plus 2y equals 5, so that's just a line. And then in 3D, so 3x plus 2y plus 4z equals 5. And guess what that is? It's a plane in the 3D space. So now let's do one example like this. So let's say we do have 3x minus 4y plus 2z equals 24. So what you want to do, you want to find the x-intercept, the y-intercept, and the z-intercept. So once you're being able to get all those x, y, z intercept, all you need to do, you just need to plot the points. So in order to get to the z-intercept, so we set x, y equals 0, so 2z equals 24, so z is 12. So we got 0, 0, 12. And then for the y-intercept, we set x and z equals 0, so we do have y equals negative 6. And then 0, negative 6, 0. And then for the x-intercept, we set yz equals 0, so we do have 3x equals 24, so x is 8. So the sign like that, that means then or therefore. So we got 8, 0, 0. Plot the point, so here's what we found. So 0, 0, 12, and then 0, negative 6, 0, so it's to the left on the y-axis, because that's negative. And then for the x-intercept, we got 8, 0, 0, so it's 8 unit forward. So as you can see that once you connect the dot here, so it's a triangles in the three-dimensional space. So you see that the red shaded region here, so it's a regular triangle in the three-dimensional space. We can say that's a scaling triangle because all three sides are different. So now you want to grab that 3x plus 4y equals 12. So notice that this is a linear equation. So this graph in the xy, well, in the plane, it's a plane in the 3D space. So in 2D, so the graph is x equals 3. It's just a line. But now in the three-dimensional space, so this one turns out to be a plane. So let's start out with x equals 0. So we solve for y. So we do have 0, 3, comma z, because we don't know what z is. And then set y equals 0. So we do have 4, 0, z. So a plane that is parallel to the z-axis, because we don't know exactly the value of z. So that means those two line segments there, they got to be parallel. Same as the upper line segments. So we just plot the point. So it's 3 units on the y-axis. And then over here, which is 4 unit forward. So once we connect the bottom base here, and then we structure the same thing on top. And then for the z-axis, you can go as far as you want, all the way to the top. Or you can go all the way down to the bottom. So you can say that this one's kind of like a square, but actually it's a rectangle. Okay, so it's a rectangle. If you try to extend it all the way down here for the z-axis. Okay, so it can be a rectangle. So this one, it's a two-dimensional plane in the three-dimensional space. Okay, so that's it. So here's the lesson, what we got for the three-dimensional space with the Cartesian coordinates. And it's a good lecture for multivariable calculus. It's like early introductions. So the early preparation for students who want to take multivariable calculus in college. Okay, so I'll see you guys next time.